Geometry Unit 14, Section 3, chord segment lengths. If a diameter of a circle is perpendicular to a chord, then it bisects the chord. So there needs to be a second bullet point here. This is one statement. If a diameter of a circle is perpendicular to a chord, then it bisects that chord. So we see here that DE is a diameter. It's going through the center of the circle C. AB is a chord. If they are perpendicular, that means the chord is bisected. It doesn't mean the diameter is bisected. It means the chord is bisected by the diameter. So what we would get here is AF is congruent to FB. And so that can be, used to create right triangles, congruent triangles, something to do with, midpoints, bisecting. So that's an important relationship to know. It's the first property about chord segment lengths is that if the chord is perpendicular to a diameter, it's getting bisected by that diameter. Statement number 2, if two chords are congruent, then the center is equidistant from the two chords. So what we're saying here is that chord AB and chord CD are the same length. What that means is they must be the same distance to the center of the circle. So what we're really saying here is because AB is congruent to CD, therefore OE is congruent to FO. And that means that this is congruent to this. And this is not a radius because it's not going all the way to the edge. It's going to the chord. But because the chords are the same length, and that should kind of make sense when you think about it, because a chord, the only way to make a really long chord is have it close to a diameter. The further away from the center we get, the smaller the chord gets. So, a chord of this length, the only way to have that is by this distance. Even if I'm on this side, it's still, if I want it to be the same length, maybe make this a little bit smaller. Um, whatever this distance happens to be, if I were to move this over to here, it's going to be that same distance away because of its size. So that's really what this is saying. This is not something that really comes up often, to be honest with you, but it is a chord property. All right, so now we want to explain, this is a little cut off, why triangle CHO, this triangle over here, is similar to DRO, this triangle over here. Why are they similar? Again, through angle like we did in the previous video. Well, first I have reflexive angles over here. I'll call them 1 and 2 just to save a little bit of time. Angle 1 is congruent to angle 2 because of a reflexive. And then also what we did similar in the last video was we see that this is an inscribed angle opening up to arc HR, and this is an inscribed angle opening up to that same arc HR. And the same can be said for this angle and this angle. They both open to the same arc, so we can really see this as angle, 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 but we know we only need 2. So angle C is congruent to angle D. Now, if this was like a statement, reason, proof, what would I say? I'd say something along the lines of inscribed angles that open to that intersect the same arc are congruent. Something like that would work. So true or false? CO to over DO. CO over DO. Now, those are corresponding lengths, CO and DO. They're not the same length. They're not congruent, but they are corresponding lengths. So that means they're proportionate. And OH to OR, they again are corresponding lengths, so they are proportionate, so this is true. And then cross multiplying again, this is true. This is the same kind of setup as the last video where we tried to get you to show why the concept for a secant was like whole times exterior equals whole times exterior of the other secant. Well, for two chords, the major property we see in two chords is something I like to call part times part. And basically what we're saying is CO times OR. And you see that CO and OR are the two parts that make up chord CR. Well, those two parts, the product of those two parts equals the product of these two parts, HO and OD. So the product of these two parts, this part times part, equals the product of these two parts, part times part. And that's really what the major chord segment property is, and that's what we're saying here. Part 1A times part 1B, and so on, so on, so on. But if I put little labels of A, B, C, D on it, you see that A times B, this times this, A times B equals this times this. The two parts of one chord multiplied equal to the two parts of the other chord multiplied. So for a quick example, we see here 4 and 12 are the two parts of this chord, so that's 4 times 12 equals, 6 times x. 6 times x, that's 48 equals 6x. So x equals 8. Um, it's really pretty quick, pretty easy algebra there. All right, how about another one? In the figure, circle P has a radius of 10. Okay, so that means that PE is 10. That's a radius of 10. That also means that DP, this whole thing, is 10. So remember that. AB is perpendicular to DE. So this is a chord that's perpendicular to the diameter. And what that means is the chord is then bisected. If AB, if this whole thing equals 8, if the whole chord is 8, that means its two parts would be 4 and 4. What is the length of AC? Well, there we go, 4. Then part B, so what I think what they're doing here is they're using the same concept of radius 10, but ignoring, this question up here. So let's pretend we don't have 4 and 4 here. If DC is 2, what is the length of AB? And so what we have to realize here is that, well, if DC is 2, that means that CP must be 8 because the radius is 10. So together they are the same thing as a radius 10. But how could I get this length? And this question, this has come up a couple of times, and it's actually a very easy question if you know the trick. And the trick is to draw an auxiliary line. Draw an auxiliary line, an auxiliary radius. And what I know about this radius here is it is length 10. So this is 8, this is 10, this is perpendicular. So this is the third side of a, 6, 8, 10. It's going to end up being 6 Pythagorean triplet triangle there. So because this is 8 and this is 10, this has to equal 6. And if that equals 6, then AB, that whole thing, is 12. So, I mean, if you don't know the 6, 8, 10 triplet, you could, of course, do Pythagorean theorem of, x squared plus 8 squared equals 10 squared. But you see this happen a lot with a chord perpendicular to a diameter. You could draw in an auxiliary radius to turn it into a right triangle if it's not drawn for you, and you know the radius length. And so this kind of comes up a good amount. So that's really it. I mean, the chord bisected by a diameter when it's perpendicular, that along with the simple just part times part equals part times part product algebra is really not too bad. So that's really it for chord segment lengths. Pretty easy concept, probably the easiest thing in this chapter. All right, short one. See you.